Hi everyone, we are starting the alcohols and phenols chapter, and this will be chapter 12 in the third edition of the textbook and chapter 13 in the second edition of the textbook. Now down below I have a little chart showing different types of alcohols. So we have primary, secondary, and tertiary alcohols. And this is very similar to how we would determine if we have a tertiary, secondary, or primary carbocation or radical. It really depends on the carbon and how many carbon groups it's bonded to. So if the carbon that the alcohol group is bonded to is only bonded to one other alkyl group, then it's a primary alcohol. If the carbon that the alcohol group is bonded to is bonded to two alkyl groups, that's secondary. If it's bonded to three, it's tertiary. So just some terms to keep in mind. Now first, we're going to start with nomenclature. How do we name alcohols? So it's pretty similar to how we would name alkanes, alkenes, and alkynes. You first want to identify and name the parent chain, then identify and name any substituents, then you'll assign a number to each substituent, so a location, and then you'll list the substituents alphabetically. Okay, so let's look at an alcohol, and let's look at one that's not too bad to name. All right. And then let's look at another one that might be a little more difficult to name. Okay. And finally, let's look at one that has a stereocenter. All right. So let's start with the first alcohol. So again, the first thing we want to do is identify and name the parent chain. So let's count our carbons in the longest chain. 1, 2, 3, 4, 5. And we want to make sure that the alcohol group has the lowest number possible. Luckily, this molecule is symmetrical, so either way we number it, the alcohol group is at position 3. Okay, so would we say, let's see, pent for 5? And normally we would write pentane if this was an alkane, right? But for an alcohol, what we're going to do is get rid of the E, and then we're going to add OL for alcohol. Now, because the OL is indicating that we have an alcohol, the only other thing we need to do is list the location of the alcohol group. So that's on carbon 3. So we'll just write 3-pentanol. Now, there is another way that you could write this. You could write let's see, pentane 3-ol. So you could put the 3 in front of the OL. Whichever one you prefer is fine. They're both correct. Okay, let's look at the next one. So let's see, we've got an OH group on a 5-membered ring. How would we name this one? So if you ignore the OH, how would we name that ring structure? So the ring structure we would call cyclopentane normally, But because there's an OH group, we're going to replace the E on the end of cyclopentane with OL. So cyclopentanol. And we don't have to list a number for the alcohol group because it's just assumed that it's at position 1. So now let's carry that down into the next molecule. So again, we have cyclopentanol, but we do have a couple of substituents off to the left. Now, how would we number everything on this ring? Well, first of all, the OH group takes precedence over any other of the functional groups, so that would be at position 1. And then we just want to number the methyl groups so that they have the lowest number possible. So I'm going to go up and over, so 1, 2, 3, because if I went the other direction, the methyl groups would be at position 4, but we want them to have the lowest number possible. Okay, so then we would write 3, 3 dimethyl in front of cyclopentanol. And again, remember, even if both of your methyl groups are at the same location, you have to write that number twice. It seems redundant, but that way you're really letting someone know both of these methyl groups are at the same location. Okay, now let's take care of our stereocenter. So this is not a symmetrical molecule. So the carbon that I just wrote an asterisk next to is a stereocenter. It has 4 different groups bonded to it. And I'm just going to draw in the hydrogen because it's in a wedge position, which will affect our stereochemistry assignment. Okay, so let's figure out whether this is an R or S stereocenter. What would have first priority? The oxygen. That has the heaviest mass. And then that stereocenter is also connected to 2 carbons and a hydrogen. And the hydrogen is, or has the lowest atomic mass, so that will be priority 4. So now we have to figure out, okay, between those 2 carbons, which one has higher priority? Well, these 2 carbons are both bonded to 2 hydrogens and another carbon. Okay, so now we have to go down the chain a little bit further. So if we're comparing the carbon up above, that is bonded to 2 carbons plus a carbon down below. This carbon is bonded to 2 hydrogens and a carbon. Okay, so it looks like the carbon up above at position 2 will have second priority because as we move down the chain, it was bonded to heavier atoms than our other carbon down below, which has priority 3. All right, so now let's draw a circle from 1 to 2 to 3, and is that going to the left or to the right? To the left. So we would assume that this is S, but hydrogen is coming out towards us. So that means we have to flip it, right? So if the lowest priority group is coming out towards you, your assignment is actually the opposite. So this would be R. So we'll put R in parentheses in front. So this is R33-dimethyl cyclopentanol. Okay. Now, one more thing that we should know when we're naming is this structure. So we have a benzene ring with an OH group coming off of it. This has a common name, phenol. And this is present in a lot of different chemical structures, even in, for instance, biological structures. So it's a pretty important molecule. Now, let's see, how would we name the following? How would we name that? So we know that we have phenol, which is the benzene ring with the OH group attached. So now we just have to name that chlorine substituent. Now remember, the OH group is assumed to be at position 1. And I'm going to number the ring so that chlorine has the lowest number possible. So it's at position 3, so we'll write 3-chlorophenol. All right. So naming alcohols is pretty similar to how we would name any of the other molecules that we've covered so far, such as alkanes, alkenes, and alkynes. All right. So now let's review a little bit of physical properties of alcohols. So let's say that you have the following 3 molecules. So this is ethane. And then we have, let's say, a similar molecule, but one of the hydrogens has been replaced with a chlorine. So this is chloroethane. Chloroethane. And finally, let's say we replace that chlorine with an alcohol. So let's just compare these molecules based on their differences. Oh, and sorry, this last molecule is called ethanol. I forgot to name it. Now, which one of these would you expect to have the highest boiling point? So let's think about the types of intermolecular interactions that these molecules would have with copies of themselves. So let's say we have a bunch of ethane molecules just kind of mingling around a beaker. What type of intermolecular force would hold those molecules together? Would it be London dispersion forces, also known as van der Waals forces? Would it be dipole-dipole interactions or hydrogen bonding? Dispersion forces, right? Because we don't have any polarity here on ethane. Okay, what about chloroethane? What would hold chloroethane molecules together in a beaker? Would it be dispersion forces, dipole-dipole interactions, or hydrogen bonding? So is this molecule polar or non-polar? It's polar, right? Because chlorine is electronegative. So that would mean that chloroethane molecules would be held together by dipole-dipole interactions. And finally, let's look at ethanol. Would ethanol molecules be held together by dispersion forces, dipole-dipole interactions, or hydrogen bonding? Hydrogen bonding. Remember, hydrogen bonding occurs if you have an H or a hydrogen between either fluorine, oxygen, or nitrogen. So I like to say hold the phone, F-O-N, to remember that one. And now that we know the types of intermolecular interactions that are going on for each molecule, which one would have the highest boiling point? Ethanol. So ethanol has a boiling point of 78 degrees Celsius. Chloroethane has a boiling point of 12 degrees Celsius. And then ethane has a boiling point of negative 89 degrees Celsius. All right, so as those intermolecular forces get stronger and stronger, the boiling point goes up. All right, so just a bit of a reminder of some physical properties here for alcohols compared to other molecules. Now, in the next video, we're going to discuss some acid-base chemistry, as well as how to form what are called alkoxides. And then we'll start getting into how to prepare alcohols, which will be a bit of review. So I will see you in the next video.